The next talk is about sharing reusing points to analysis, and it's given by Shashin. Please go ahead.
Thank you, Anders. Hello, everyone. Good morning, and thank you for joining us here today. My name is Shashin, and I'm going to talk to you about our work titled The Art of Sharing Points to Analysis. This work was done during my MS at IIT Madras in collaboration with IBM Canada Lab. It's also my very first time attending a conference. I'm really excited to be here, as you can tell. So points to analysis, as we know, is one of those program analyses that have a wide range of applications in the world of program understanding. When deciding to choose from one of the many flavors of points to analysis, or PTA for short, there are a few considerations that we end up having to make. On the one hand, you can pursue efficiency and then choose one of these really fast order of n magnitude PTAs while sacrificing precision. On the other hand, you can pursue precision and adopt a full fixed point based PTA while incurring the performance hit, because many of these fixed point based PTAs tend to be of cubic complexity. However, what if we do not want to make this sacrifice? What if we do not want to make this trade-off? What if we want to use a high precise PTA in a performance centric compilation environment like a JIT compiler, for example? This is precisely what our work hopes to achieve, and hopefully I convince you of that capability today. Our work primarily focuses on languages like Java that have a multi-stage compilation system. And the most natural, simple solution for this balance that we want to achieve looks like this. We offload the responsibility of performing the expensive fixed point PTA to the static compilation stage, which then bundles the result of that analysis along with the bytecode and puts it aside. And then when the JVM, which has the JIT compiler associated with it, when it picks up the bytecode, it also gets these PTA results. And what it will do is it will just blindly use it in its optimization path like any other compiler would, right? This has been studied extensively in literature. It has been given various names, but we know of it as stage analysis techniques. It has quite a few names. However, all of these techniques raise a very important question, the question of trust. How does the JIT compiler in this case, how does it trust that the analysis results bundled with the bytecode are actually for that program under compilation? How does it trust that it has not been tampered with, either over the wire or at the source during encoding itself? This is the concern that our paper hopes to address, and again, I hope that I convince you that we are able to do this. Now, going forward in this paper, whenever I refer to PTA, I refer to flow-sensitive, context-insensitive points to analysis. Okay? Also, before I proceed, I'm going to introduce two terms which I'm going to throw around a lot. I'm going to use the term producer to refer to that compilation stage which becomes responsible for performing the expensive analysis, and then transmitting it to the stage that needs the analysis. I'm going to use the term consumer to refer to that compilation stage which is performance-centric, cannot afford to do these expensive computations, and therefore will consume these results that it receives from the producer. Let's spend a second just understanding this issue of trust and then convince ourselves that it is indeed something worth talking about. A JIT compiler should not trust the results of any analysis that it does not perform by itself, right? As a compiler, it should not be taking any compilation decisions, any optimization decisions, unless it is based on the code or something it can infer about the code by itself, right? Let's try to work towards this goal in the rest of this talk. So basically what this means is if we want to accomplish this guarantee of the compiler and also work in the context of stage analysis, what we need is to give the JIT compiler the capability of checking the soundness of these analysis results that it obtained from the producer stage, as we termed it. So let's talk about the key insights which will kind of establish the core technique of our work. When an IDFA-styled PTA terminates, the results represent one of many possible fixed points for that program. And each of these fixed points corresponds to a points to analysis result, which is consistent with the program. And because it is consistent with the program, it is safe to take decisions based off of it. It is safe to perform optimizations based off of it. This forms the basis of our first key insight. We expect the producer stage to send to the consumer stage PTA results which corresponds to some fixed point of the program. And because of the premise we just established, in order for the consumer to check that this is in fact consistent and safe to use with respect to the program, all it has to do is check if it is a fixed point or not. And fixed points come with this very interesting, rather trivial mathematical guarantee that if you recompute a fixed point value by applying the same transfer functions, it should not change. And the consumer can simply assert this property as its safety check, right? Let's look at an example to ground ourselves of this fact. Here's a simple Java program snippet. It consists of a linear sequence of allocation statements followed by a non-deterministic loop, which itself contains a couple of assignment statements in its body. Line number 8 here is what we call a loop header, right? Here we have what we call a points to graph. This is a graphical representation of the points to information at the loop header after the points to analysis reaches fixed point. We use out of S8 to denote it, and what it shows is basically the heap objects that are pointed to by the program variables, and also the heap objects that are reachable through the fields of those respective heap objects. And by virtue of how data flow analysis works, computing this out of S8 incurs a fixed point computation. You need to analyze the loop multiple times in order to obtain this. And going back to our performance considerations of the JIT compiler, this is something we do not want to do in the JIT compiler because it becomes part of your runtime overhead. So based on our staged analysis paradigm that I introduced, this is naturally one of the things that we would expect the producer to take responsibility for, compute, and then transmit over to the consumer side. Now, let's revisit our threat model, right? We said the JIT compiler cannot trust what it has received from the producer. Let's assume, for argument's sake, that the transmitted information has been tampered with in this manner. One of the edges in that points to graph has been removed, and now it conveys a completely different meaning. It is not consistent with the state of the program at line number 8. So the JIT compiler needs capability to detect this, right? This is our first contribution. So let's look at how the JIT compiler can actually catch this tampering. So like I said, this is the result of a terminated fixed point PTA. And because of that, this represents a fixed point value for the program, or at least it is claimed to represent a fixed point value for the program. And if you were to compute out of S8 one more time, if you were to recompute it on the consumer side, this should not change. That is the invariant that we hope to check, and that forms our safety check, right? Let's try to see if that is in fact true. Let's try to trace that. So the way this would work in a data flow analysis is you use the supplied out of S8. You would set that as the initial outflow value of the loop header. And then you would propagate that value through its control flow successors. In this case, it is lines 9 and 10. At each phase, you would apply your transfer functions according to your analysis that you're using. And then by virtue of control flow succession, you're going to propagate it back to the loop header, at which point you will take, you would apply the meet operator, and you would have recomputed out of S8 again in the JIT compiler. And that looks like this. Let's draw some inferences based on what we recomputed. So if we were to compare it with what was originally received from the producer end and what was claimed to be a fixed point, we observe that it is immediately different. The recomputed out of S8 now has a new edge. It contains new information that wasn't in the originally transmitted out of S8. Now the direct inference here is that what was originally sold to us by the producer was in fact not a fixed point for that program because it changed when you recomputed it, right? This forms the basis of the safety checks that we propose in our work. So you are given something that is guaranteed to be a fixed point, you recompute it once, you observe whether it is a fixed point or not. If it is not a fixed point, you draw the inference that this is not consistent with the program and therefore it is dangerous to use it and perform optimizations or take compilation decisions based off of it, right? I'm going to hammer a fact a couple of times here. Remember that we have performance considerations in the JIT compiler. We don't want to analyze any program statement more than once. And if you notice here, in order to detect tampering, we only processed rather each program statement exactly once and no more than once, right? But wait, there's more. As it turns out, we get an interesting additional capability for free while attempting to detect this tampering. So if you remember how we kind of recomputed out of S8, when we went through the loop body, we also computed out of S9 and out of S10, right? And let's say for argument's sake that the original out of S8 sent to us by the producer was not tampered with. Let's say it was a true fixed point. Then this out of S9 and out of S10 that you would have computed will also necessarily be fixed points by virtue of how data flow analysis works. What this means is that the producer does not necessarily need to send the consumer data flow values for every single program point in the program. It only needs to send it for certain key program points. In this example, that key program point happens to be just the loop header and nothing else. So given just the loop header's fixed point information, we are able to kind of compute the fixed point information for all the other program points by a simple application of data flow analysis rules. This forms the basis of what we call artwork in the paper. It is a concise encoding of points to analysis results for a program. Now, the ideas we have seen so far support the detection of tampering and regeneration of flow-sensitive intra-procedural PTA. In order to extend this to the inter-procedural dimension, obviously we want to handle function calls, both recursive and non-recursive. So in this talk, I'm going to focus on non-recursive in the interest of time. Remember that the performance goals again mean that we want to analyze each statement exactly once, no more than once, and by extension, that means we also want to process each method exactly once. Not only that, the consumer has to analyze each method in such a way that the computed summary of that method is now usable across all of its call sites, because otherwise you'd end up having to recompute it for each new call site in the program. Now, if we want to do this for the context-insensitive PTA that we're dealing with, invariably this means dealing with more fixed points by virtue of how context-insensitivity works. So we need a way to address this. So we'll talk about that next. So the next set of key insights are coming up. In the world of program analysis, if you analyze a method starting from its context-insensitive in summary, you're guaranteed to end up with its context-insensitive out summary. And by construction, the context-insensitive out summary of a method is going to be valid, applicable, and sound to use at every single one of its call sites across the program. So, for argument's sake, let's say we convince the producer to send the consumer the in summaries of every single method in the program. Our job is done, right? The consumer just needs to use it, and then you're done. Everything's good. That is true, but now all you have done is you have introduced another item, another data item that the JIT compiler cannot trust, and it needs to check the soundness of, right? So let's look at how we do that, and this is best explained pictorially. On the left, we have a statement labeled S, which happens to be a call site for the function foo. On the right, we have a pictorial representation of the function foo. Remaining on the right, in of foo is that context-insensitive in summary that I just described, which is kind of sent by the producer based on the premise that we just established. What the consumer does is just the following. Applying the ideas we have seen so far on the control flow predecessors of S, it deduces the inflow to the statement S, what we denote as in of S here, and it simply checks whether this inflow is consistent with the context-insensitive in summary that was sent to us by the producer. And if it finds that it is, it will use that same context-insensitive in summary to compute the out summary for foo. And because of the premise we just established, this is guaranteed to be context-insensitive out summary for foo. And by virtue of that, what it means is we can use that to compute the outflow of statement S. So if you notice, what we have done is we have kind of stitched together invariant that was sent to us by the producer with some data we inferred at runtime in the consumer, right? Let's again look at an example to ground ourselves that this works. Here's another program snippet. It contains 2 call sites on line 7 and 10, both of which invoke foo, but with different contexts, right? And on the upper right, we see the context-insensitive in summary for foo, and this has not been tampered with. This is a true fixed point. You can take my word for it. And if you also just glance at it for a while, you'll be able to see that the inflows at both the call sites are consistent with that context-insensitive in summary because it has not been tampered with. Because of which, if the consumer computes the out summary using that in summary, this is what you end up with. This would be the out summary, and it can be trivially seen that this out summary can be used at both of those call sites because it is sound, and you can compute the outflow values of both of the call sites. So effectively, what we have achieved is we have performed literally interprocedural context insensitive points to analysis by analyzing each call site exactly once, and by also analyzing the concerned method exactly once. So we are still sticking to our performance goals, right? For completeness sake, here is what a tampered context-insensitive in summary would look like. Clearly, this does not kind of contain the inflows at either of the call sites. The edges have been redirected. One of the objects is supposed to be null, and that does not reflect that. So this is something that the JIT compiler can very easily detect by just simply identifying that the inflow is not consistent with that. Right? So that's how we detect tampering of the context-insensitive in summaries. So taking a step back, let's take a bird's eye view of what we've done. This is what our system looks like. The same producer and consumer. We augment the producer with what we call an ART encoder, and we augment the consumer with what we call the ART regenerator. So ART is short for Analysis Results Representation Template. The purpose of the ART encoder, and by extension the producer, is to basically encode a concise representation of your PTA results, what we like to call artwork, and bundle it with the bytecode in the case of Java, right, and then set it aside. And the ART regenerator is responsible for applying all the ideas that we just saw, check the soundness of the encoded results, and if found to be safe, it kind of rehydrates the points to analysis for the whole program, starting from those key program locations, and sends it along to the optimization pass of the JIT compiler to be used like any other compiler would. Also in the paper, you'll find a detailed discussion on the support for recursion. We also offer detailed algorithms for checking the safety and regeneration. They're supplemented by pretty easy to follow along examples if you'd like to take a look at it. We also provide proofs of correctness, and we also discuss a subset of very simple optimizations that you can do to further increase the efficiency of encoding. In terms of implementation, we use a suite-based static analyzer as our producer, and we instantiate two consumers, one of which is a suite-based static analysis client, and the other one is the JIT compiler associated with Eclipse OpenJ9, which happens to be a production-grade JVM. And we evaluate against a set of benchmarks from SpecJVM and Dakapo. Perhaps unsurprisingly, regeneration is really quick. On average, we see that regeneration takes like a little over 0.5% of the time that the whole program fixed point analysis would take. And we do this with around a 10% overhead in terms of per method JIT compilation time. And we also see a roughly 4% overhead in terms of the bytecode size. The final interesting experiment we did was to see how the availability of these results affects a production-grade JVM. So what we did is we introduced these results into the Eclipse OpenJ9 JIT compiler, and we augmented its function inliner to use it. And we were able to see observable improvements in execution time, a selection of which is shown here for a couple of benchmarks. Given that a JIT compiler is already insanely optimized, any performance you can claw back from it is considered noteworthy. So to quickly summarize, what we have achieved is a way to efficiently realize precise, sound, flow-sensitive, context-insensitive PTA results in a performance-centric environment while maintaining the invariant of trust. We offer solutions to both intra and interprocedural analysis, and we also account for recursion, so nothing left out. We offer proofs of correctness and also an extensive evaluation which looks at both the metrics, efficacy, and usability of the technique. In conclusion, I'd like to thank all of you for attending again. I'm currently a student at UT Austin, so if you're in the neighborhood, please feel free to come by and say hi. Happy to take questions. I'm a little over time, Anders. Thank you for understanding.
Thank you. Any questions? So I would like to know, is there any particular reason why you choose a flow-sensitive analysis? Would this also work for flow-insensitive points to analysis?
So that's a good question. So we believe that flow-sensitive offers a dimension of precision that you cannot get with flow-insensitivity. Specifically, if you choose things like function inlining, right? You want very localized information. What is the state of the points to information at this particular program location, and whether I can take an inlining decision at a particular programming location, at that particular program location. If you're maintaining flow-insensitive analysis, where you have analysis, where you're maintaining points to information at a method level, you tend to be overly conservative, and you might end up missing some opportunities to inline. It might be difficult to identify a monomorphic call when it is actually monomorphic. So which is why we decided to use flow sensitivity, because it simply offers more granularity and precision.
But it would also work for flow?
Yes, this should trivially work with flow insensitive as well. Yeah.
So another question, if there are no other questions from the audience here. What about dynamic class loading? So you seem to have this whole program assumption so that you have the entire code available to do the analysis.
So, then you can that is a question which came up a couple of times. Thank you, reviewer B, if you're in the audience. So there is interesting work being done about that. We don't deal with it, but there is work which deals with how do we handle it when the underlying program representation changes. Could be because of dynamic class loading, could be because of optimizations which would have run and changes the underlying program abstractions. So we don't deal with that here, but there is work being done on that in terms of like maintaining the points to analysis to kind of reflect the updated code.
Okay, thank you again.
Thank you very much.